So good afternoon, everyone. So thanks for the introduction. I'm Karol Desnos, and today I'm going to present a collaborative work with several PhD students, master students, and several colleagues. And the work is entitled Ultra-Fast Machine Learning Inference through C Code Generation for Tangled Program Graph. So not deep learning. So what are we talking about? Yeah, sorry. So a tangled program graph is a graph, and it is a reinforcement learning technique, which we will call for short TPG. And this reinforcement learning technique was proposed by Stephen Kelly and Malcolm Haywood back in 2017. In this machine learning technique, you represent your learning algorithm with a graph, which consists of a set of vertices, which we will call teams, a set of leaf vertices, which we'll call the actions of the graph, and a set of edges, which we will call the programs of the graph. In order to understand how the TPG algorithm works, we need to understand first what a program is in this kind of algorithm. So let's have a look at what is inside a program. A program of the TPG can be seen as a black box algorithm. It receives a copy of the state of the environment, an observation of the environment. It processes this copy of the environment, and it produces a bid, a number, the floating point number called a bid. Don't try to make sense of this number. It has no sense. It will have a sense just because it will be compared to other numbers. But it is not a probability. It is just a number. If we have a look at what's inside the program, it is quite like an assembly program. So we have a sequence of instruction, assembly-like instructions that will take as operand the features from the learning environment and the result of previous instruction. The result of the last instruction of the program is the output of this program. So we have an assembly-like program. So how do we use this program within a graph? Each time we want to run an inference of the TPG, we receive a new state of the environment, and we start the execution of the graph from the root team of the Tangled program graph. So we start from this root team, we execute all programs on the outgoing edges of this root team. So we run these three programs. Each program produces a bid, a number, and then we will compare these numbers and we will select the largest one, which will be the winning bid. And we will continue the execution of our algorithm following the path indicated by this bid. So in this case, we will move to the following vertex, the following team of the graph, execute the program on its outgoing edges, identify the winning bid, and eventually we will reach a leaf of the graph, which is an action of the graph. This action is associated to an action of the TPG on the environment, which will cause a change of the state of the environment. We will thus receive a new state, updated state of the environment, and we will start again the inference process from the root team of my graph. So this is how the TPG graph works in inference. In order to train the Tangled program graph, we use a genetic programming method. So based on a pseudo-random number generator, we will have a way to mutate the graph topology, but also the instructions of each program of the graph. And so based on a genetic evolution process, which I will not detail because I don't have enough time, we will actually build from scratch a graph that is dedicated for each learning task that we are trying to tackle. So how does this work? Does it work well? Yes, it works quite well. TPG has been extensively tested on video games environment, on the arcade learning environment. And it has been shown that the TPGs are a very efficient learner. They have an adaptive complexity because when you are growing the TPG graph with the genetic programming method, you get a topology of a graph that is well suited, that is perfectly suited to the complexity of the task that you are trying to tackle, as opposed to classical deep learning techniques like deep Q-learning methods, where the topology of the deep learning network is usually chosen by an expert data scientist that will try to find the best graph possible. Then it is also very fast. On similar hardware, so without a GPU, to be clear, TPG runs 2 to 3 orders of magnitude faster than a deep Q-learning network with an equivalent fitness in the learning environment. So TPGs run much, much faster. Finally, this model, the TPG model, is very, very lightweight. In order to store all the parameters of a trained TPG graph, we need roughly less than 100 kilobytes, compared to usually more than 50 megabytes for equivalent performance for a deep learning model. So TPG is very interesting because this is very low complexity. The complexity is adapted to the environment, and the model is very lightweight. So these are the introduction. Now, what is our problem? What is the problem we try to solve in our paper? When you want to train a TPG, you have a learning environment, you have the TPGs that you are trying to grow, and you need something in the middle, which is a TPG training framework. In our case, we are using the JJLIT open source framework that we are developing to train the TPG. And so this framework is used both for training the TPG, so to connect the TPG that we are training to the environment, and also to do the inference in order to evaluate each new generation during the genetic evolution process. The issues that we have is that we have an overhead because of this framework in the middle. In order to have an evolvable TPG, so a tangled program graph within which we can add and remove vertices during the genetic evolution process, or a TPG within which we can move, add or remove programs, so edges and vertices in the graph, we need to have a flexible structure. And this flexible structure has a cost because it needs to be able to add and remove things. So it has an overhead. On the execution side, when you want to infer a TPG, you also have an overhead because all the programs within the TPG are also dynamically constructed programs. So you need to be able to add, remove, and alter the instructions of each of the program of the TPG. And this has an overhead. In particular, you need, once again, a flexible data structure to store and modify the structure as you wish. But you also need to implement a runtime software fetch and decode mechanism, similar to what you could do in hardware for an assembly language. Here you have to do this in software to decode the instruction, fetch their operands, and bring them to the TPG in order to execute the program. So all of this has an overhead on the performance of the TPG execution, and this is what we are trying to get rid of. So how we will do that? To do that, the solution that we propose is to get out of the framework that we have proposed to train TPG. And once you are satisfied with the TPGs that you have obtained, so after the training process, the idea is to have a code generation mechanism that is able to generate some standalone C code, standard C code, that you can use to infer the TPG, the trained TPG, directly in the learning environment without requiring all the overhead of the training framework. So if we have a look a bit under the hood of how we do that, the inputs that we have are first the set of instructions that we can use in our TPG model. So each time you want to train a TPG, you can actually specify the set of instructions that you want to use to train the TPG. And to specify an instruction, you will use the piece of C++ code that looks like this, where you specify your instruction, you specify the type of parameter it will take, you specify how it will run when it is run within the C++ framework, and you will also specify templates for a code generation. So each time I am encountering this instruction in a trained graph, I know that I can use this kind of regular expression template to generate the C code for the standalone inference code. So if I combine this instruction model and template and the program of my trained TPG, I can generate a piece of C code that corresponds to the behavior of the program. So I will generate one function, one C function per program, which receives a pointer to the state of the environment. And then I have to declare the registers that will be used by my program. And then each instruction of the program will be translated in the corresponding C code. So here I see that I have this instruction, which is a call to the exponential instruction. And here I am retrieving the data from the environment. And on the line below in orange, I am actually calling the function using the C++, the C template, the code generation template that I have declared when I specified my instruction set. And at the end of the program, I will return the result of the last instruction. So this is for converting a program into C code. Now, what about the graph? You also have to transform this graph, the topology of the graph, into C code. To do that, you will first have an infinite loop, which corresponds to the call or to the program starting to the TPG starting from the root vertex. And inside this while loop, you have a switch, and this switch makes it possible to execute the different teams of your TPG. So you have a case for each node, each vertex of the graph, cases for the teams, and also cases for the action. For each team, you will first generate the call to all the programs on the outgoing edges of the team. So here, for example, if I'm generating code for this team, I have 2 outgoing edges. And so I will call the 2 programs corresponding to the outgoing edges of this team. Then I will identify the program with the maximum bid, the largest bid. And this will be used to select the following teams that I will use in the next iteration of the while loop to continue the exploration of my Tangled program graph. In case of an action, I will just return the number of the action that was selected by the TPG. And so this is how the generated code looks like. We have tested this code generation on the arcade learning environment, which is a set of Atari video games. So we have tested our code generation on 5 different games, Alien, Asteroids, Centipede, Fishing Derby, and Frostbite. And these games are interesting because they have quite different complexity. So here I am showing just the average number of teams and programs in the TPGs that we have trained. There is actually a lot of variance in this number. So these are the average, but the variance that you can find in the paper are quite high. So you have a very diverse graphs in this learning environment. We have deployed the generated code on 4 different hardware targets: an Intel Xeon processor, an Intel i7 processor in a laptop, and 2 embedded platforms, Jetson TX2 without using the GPU. Once again, we are only using the multi-core architecture, and a Raspberry Pi 2 with a low-end ARM device. What are the results? So the first result that is interesting in our experiments is to see the speed up that we have when we compare the inference time using the framework, using JJLATI, our TPG training framework, and using the inference code that was generated with the tool. And so for each of the platform, we present the different speed up that we had. The results are presented for each game that we trained on. And as you can see, we have on average a speed up of 45 on the Xeon architecture, a bit more than 25 on the laptop, around 45 also on the Jetson architecture, and on average 85 times faster with the generated code that when we are using the framework when you are on the Raspberry Pi 2. So we have a huge speed up when we get rid of the framework for training the TPG, for inferring, sorry, the TPG. A second interesting result is when we tried to measure the time it takes to run every single instruction when running the different when running the TPGs, the inference code, the generated inference code on the different platform. And here we have 2 figures presented for each platform. We have in green the inference time with the generated code, the C code, and the inference time in red when you run the inference within the library. And why these results are very interesting? They are very interesting first because the time it takes to run any instruction is very small. You only have less than 10 nanoseconds in a high-end CPU, and a bit less than a bit more than 50 nanoseconds on a low-end ARM core. So this is quite fast. But the second very interesting thing is that the variance that we have on all of these figures is very small. And this means that by measuring the time it takes to to run an instruction, we can feedback this information to the training process of the TPG. And by using this information of the time it takes to run each instruction, using that with the number of instructions of a TPG, we could actually predict with a very high precision the time it takes to run a trained TPG. And by using this information in the training process, we could have a complexity-aware training process for TPG with a quite precise prediction of the runtime on a target architecture. So this brings me to the conclusion of this presentation. So in summary, what did we do? First of all, we have proposed a code generation process for a Tangled program graph, which is able to generate portable standard C code from a trained TPG. And this makes it possible to run the inference without any library. Then we have shown that the inference code that we have generated is very fast, especially when you compare it to the framework, because we go between 24 times and 85 times faster, depending on the platform, than the inference with the framework. For information, the time it takes to run one inference of the graph, depending on the platform, it takes between 0.8 to 8.6 microseconds, which is quite fast. Future work, as I said, we would like to use information of this profiling of the generated C code to have a timing-aware training process. And we would also like to try to find the best instruction set for training a TPG for a given architecture. For example, we could select a RISC-V architecture set to train the TPG to match a RISC-V architecture instruction set. Finally, last but not least, all of this work is available as an open source project. The JJLATI framework and the code generator is open source. And on the GitHub of our project, you can find the artifact with all the results and all the trained TPGs, all the logs of the experiments that we used and that are presented thoroughly in our paper. And everything is available for you online if you want to reproduce our results. Thank you for your attention. And if you have any questions, I will be very happy to answer them.
Thank you, Karol. Are there some questions? If not, I can. Yeah.
Yes, thank you for this presentation. It was really nice. So at the end, I didn't understand why you didn't choose to make an implementation on GPU and only select the multi-core.
Okay, the reason is that the kind of parallelism that you have in deep learning is that you have a very symmetric parallelism where you have a SIMT, single instruction multiple thread parallelism, where you can run several cores doing the same computation in parallel on multiple data. In the case of TPG, you don't have this. When you have a look at the structure of a Tangled program graph, if I go back a bit, here it is. If you have a look, If you have a look at the structure of a Tangled program graph, the parallelism that you have here is when you are considering one team and executing the programs on its outgoing edges, you could run these programs in parallel. The problem is that these programs may access different data and they have very different instructions. So you do not have a single instruction multiple data parallelism. So we think that this is not well suited for the GPU implementation. So we don't expect any speed up if we try to use GPU.
Yeah, okay. Makes sense. Thanks.